Cool. So, hi everyone, I'm Joel Fernandes. I work for Google, and today I'm going to talk about eBPF and all the cool things you can do with it, and kind of our journey about how we try to make it work on ARM, and how that has been possible recently. Um, Whereas on x86, it's been available for a long time. Anyway, my goal today is to kind of like show what you can do with it, and like I'm going to be a little less on the technical uh, details and more on like what you can do with it and the demos and stuff like that. But I will talk about some open problems, and maybe we can have a discussion after that. So a little bit about me. So I work in the Android kernel team on the scheduler and on tracing, pretty much. Let's just start with a little bit of background. So basically, in the kernel, you have different signals. I like to call them like you have the static and dynamic kernel trace points. You have user space static and dynamic trace points as well that you can use. Uh, and then you have perf hardware events like cycles and cache misses and stuff like that. And the perf software events like the CPU clock, which is used for sampling and things like that. So these are all like low-level infrastructure available in the kernel that provides some kind of a signal. Um, so so the next thing is about BPF. So BPF lets you write programs that can run whenever any of these signals are generated or emitted with some information. So your BPF program can, you can write a program in C that is compiled into BPF bytecode and loaded into the kernel. And the idea is that the kernel will, there's a verifier in the kernel that will make sure that the eBPF program cannot crash the kernel, so you cannot do backward jumps and things like that. So the verifier runs and the program is loaded, and then the next thing you can do is you can tell the kernel, you'd like to attach the BPF program to any of those signals I just showed you. So when those signals fire, BPF program runs, and then the result of the program would like store some information like in a map like histogram, or you can also ask for a per CPU ring buffer and store actual records that you can later parse once the program has run and everything. So what's BCC? So BCC stands for BPF Compiler Collection. It does everything I just showed you. So it sets up those signals, compiles the BPF program, loads it. It's completely self-contained. So when you use when you use BCC, the flow is like you do all this. BCC will do will use Clang to do the compilation, and then load the BPF program and all that. And then once the BPF program is attached to the signals, it's just going to be running in the kernel, and there's no return to user space necessary most of the time until you need some data from the user space. So it's running in the kernel without needing to interact with user space a lot. And that's really possible because of the amazing thing that it does. Most of the eBPF programs, they do some kind of aggregation where they don't need the whole, like, every trace record. They do this aggregation, and the records don't have to be stored. The alternative would be you would collect all your traces and then have to do some kind of post-processing of something, which can be useful if you want to do different kinds of analysis on the traces. But say you run a typical eBPF tool, you would not store all those gigabytes of traces, you would process them and then build some kind of a data structure like histogram or something. And that's really cool. Not having to do that post-processing. So that's also efficient for some use cases, like for example, say you wanted to count all the unique stacks, how many times they occur. Say in this example, count the number of stacks that led to the submit bio function in the kernel. So this is an actual tool that does that, and you can see the stack showing you that this stack occurred like 60 times. And there are many ways, other ways you can do that. Like you can use perf and then record all the stacks and then count them later. The eBPF DCC way of doing it would be to build an in-kernel histogram where the key is the stack and the value is the count. So you would not have to store all those duplicate stacks and post-process them. You have this efficient structure with the key being the stack and the value being the count. Yeah, and DCC actually isn't like replacing perf or something like that. It uses perf events and as much as possible, and does a lot with that. So it's efficient, but there is overhead. So Patrick asked me to actually measure that, and I actually measured it day before yesterday. Like, so this is perf bench get pipe running with the CPU disk tool running in the background, which actually puts a kprobe on finish task switch, which is a function that the function in the kernel that is executed during context switches. And so there is some overhead. It's not free, but how it is. These are some of the other reasons, other advantages of using DCC. So a lot of times people want to send patches that add some statistics in the kernel, and so with this you can get statistics without having to have these kernel changes that you may have to carry out a tree. The other nice thing is there's a large collection of tools that are already written out there that people can just run without understanding how the tool works a lot of times. So it's a nice, like, I like to look at it as a nice repository of tools that people can use. And they're very simple to run. Usually they have like one command line argument or two of them, or three of them, something like that. So it's a nice collection of these kinds of things. So here's a tool. Here's one of these tools, a FileTalk, which inserts kprobes on VFS read and write to show you at the VFS level all the reads and writes that are happening. If you wanted to trace that, so in this, what we have is the contacts app in Android is saving. Like you create a contact and you save that, and you can see that there's a write to that file there. So you get that observability, and being in the kernel, you don't miss anything. Versus running some other tools like strace or something. This is like a global view of all the VFS operations, reads and writes in this case, happening globally across the system.
Why was one of them bold?
I just want to highlight it. Yeah. So that's about BCC and stuff. And so now I'll talk about how we got it working on Android. So there were several issues. On Android, we don't have kernel headers on the device, which are needed by BCC to compile the eBPF program. The other issues is we don't have Clang, Python, or any of that on device. And then the Bionics C library also doesn't have things that may be needed. So the first thing I did was last year I wrote a daemon called bpfd, which would is like a statically compiled binary that sits on the device, and it receives, and you run BCC on the host, and that would send the eBPF bytecode and all of that to the daemon over ADP, and BPFD would do all the low-level things like loading the BPF program, reading the maps, setting up the trace points and kpros and all of that. And it works really well. Almost everything works. And I wrote an LW, an article explaining the architecture of that. And if people want to try it out, they're more than welcome. The second thing, so the most recent thing that I did was I used the Debian tools and some techniques like chroot and stuff like that to actually run a small Debian root file system on the Android device. And it works really well. I was pretty amazed by the functionality that it gives. There's a tool called Android.The, which packages and builds this file system and then puts it on the device. And it, you point it to a kernel tree and it extracts kernel headers, puts that into the file system, and it actually also clones BCC master and it builds that on the device itself. So it clones it onto the device and builds it there. And the really nice thing about Android.The is that you get all these other things too, they're like perf and place command and all these other tools. There's even like VI and GCC and Clang and all of that. If you wanted it, and with this, like you get all the functionality of BCC on the device. There are many advantages to doing this versus bpfd. One of the things about bpfd is like if you have tools that generate a lot of data, then it's very slow to do it across the ADB boundary. Whereas with this, it's the overhead is much lower, and it's very fast to set up. To like, if I have a tarball of a root file system that I already built, and I pushed it to GitHub releases, and it pulls it from GitHub release. It's really fast to set up. There are some drawbacks of this whole eBPF. One of the drawbacks is it takes a lot of space because it's a file system essentially, and then you also need a rooted Android device because you need to root.
You should mandate possibility.
Of course.
You should mandate that all the phones can be rooted.
Yeah.
Yeah.
I'm pretty sure increase the size of this in
So the data partition on the Pixel 2s have like a lot of space, like 100 gigabytes and stuff. So it's really the 300 MB is nothing.
gigabytes?
I think.
I think he's got 128 gigs.
Yeah.
Oh, I have that version. Yeah, probably.
Yeah.
He got much more.
Yeah.
So how do we get these phones without having to run an arm?
I didn't put too much thought into the routing thing, so I don't know. Like,
if you buy them from the Google store,
yeah.
if you get it from Verizon.
What if I get it from Five? Five's coming through.
Yeah, I think that one.
Yeah, so ever since I wrote this, I use this on a daily basis, and I have like VI running on the device, and many times I do my debugging natively of many user space tools like RTApp and even perf. I was digging into the perf code, so I was editing perf code on device, compiling it, and I was pretty amazed on the Pixel 2's perf. I was able to build perf faster on the Pixel 2 than on my IBM ThinkPad with 8 threads. Oh, so it was pretty close, like 33 seconds versus 37 seconds. The same number.
And then it got flamed.
Should be okay. Yeah, so let's so if you go to that URL. Yeah.
I mean, that's liquid nitrogen, right? It puts the phone on ice.
Yeah, ice tanks. So yeah. Okay. So that's where you could go to get more details, download it, and all that fully open source. So this is kind of like all the things, all progress that was made on ARM64 and getting Clang to build eBPF programs properly on ARM64. There were fixes that went in and stuff like that.
Did you backward all the root holes?
What's that?
Did you backward all the root hole fixes for eBPF?
No,
No?
yeah, I didn't backward those.
Okay, that's
Yeah.
But I think they want you to have sudo before you can run BPF on the platform.
Not necessarily.
No, so a while ago, there's now unprivileged eBPF here.
Yeah, no, I'm talking about this specific situation. Did you say that you needed to have?
There were a whole bunch of root holes found in BPF.
Oh,
yes.
are you talking about spectrum meltdown stuff?
No, actual
no,
number
before
root holes.
The compiler bugs?
JIT bugs.
Yeah.
Oh, okay.
I know because we had to disable and then re-enable.
Oh. The backward with the spectre.
Okay, here we go.
Okay. Yeah. So, and now I'll just show you like some common tools with the output. So this tool called hard IRQs that shows you the total time spent in IRQs across, like in this case, 10-second update. So every 10 seconds, it will show you how much time you spend, which might help you identify some like real-time issues if interrupts taking too long. So this example, I just did a test where I was constantly doing some interaction with the device, and you can see the graphics interrupts take a long time there, just to show you, and then this is a tool called cache stat, which inserts k probes in the page cache code in the kernel, and based on the frequency of those functions, getting hit by the k probe, it calculates how many hits happen, how many misses and stuff, and this can help identify performance issues related to that. If you have a lot of page cache misses, then that might be a problem. So this, I did an experiment where I dropped the page cache while I was reading a file, and you can see that the misses counter shot up drastically there. Any questions? So so for OSPM, I thought it was very relevant to do some scheduler tools as well. So there's a tool called runQLength, which uses perf to uses the perf software CPU clock to run an eBPF program a certain number of times a second. Like I think the rate is 100 times a second. And every time it runs, it's running on each CPU. And on every CPU, the eBPF program running would look at the CFS-RQ and get the length from that.
Why not put a probe on an NQ task?
Then you'll have to put a probe on DQ as well.
Yeah, but then you get actual probe counts.
Okay.
Because if you sample at 100 hertz, you can miss quite a bit.
Yeah, it gives an average idea of what the run. So this is a histogram. So the key is the run queue length and the values, the count. And if the run queue length is 0, that means that nothing is waiting. And if it's more than 0, then that means something is waiting for CPU. Yeah, we can probably do it other ways, but then there's overhead if you do it. That's so.
There's always over.
This trade-off like that, yeah. So what I did is on the Pixel 2, I ran Hackbench assigned to CPU 6 with like 8 tasks, just to force it into a situation where the run queue lengths are large and run queue length. And this right now is showing it for all CPUs. It shows what was the run queue length observed. So it's kind of a global thing, but you can do it for CPU as well. Yeah, I guess there's a slide code. Yeah, so you can see that on CPU 6, something, there was a lot of cases where the run queue length was 4. I don't know why the number, is it because Hackbench does ping pong?
Yeah, ping pong.
Okay, so 4 tasks most of the time are waiting for CPU. Yeah, that's just to give you an idea about the tools that are there. There's also a tool called run queue latency, which shows you the wait time on the run queue as well. Second, using during the Hackbench experiment, it shows you that the latencies are pretty high. You have a millisecond wait absorbed 3,000 times almost. And then you have really high latencies too, like right there. So some of these things can be done with the scheduler statistics, but then you have this stuff which doesn't need patches to do that. So that keeps the kernel code smaller as well, I guess, without having to add that to the kernel. And then this amazing trace multi-tool, which is like not a tool, not a self-contained tool like run queue length, but it's like kind of like a Swiss Army knife where you can just like write like a command line sort of a thing, and it will do what you wrote. So in this case, I'm telling trace insert a kprobe on do sys open and dump the second argument, and then it'll every time do sys open is here, it'll print that. So that's pretty cool. Like I feel like this is so much easier to use than perf to do the same thing. Like you can do it with perf as well, but using the perf probe stuff. But this is like just like one line you write like that, and it shows you all this like instantly. And you can not only do it for kprobes, all those signals that I showed, more or less you can use. So in this case, I'm actually using the static trace point for block RQ complete to dump the sectors that were part of the completed request. Showing the idle thread, I believe, because it's an interrupt that fires the RQ complete after the block IO. So that's the trace tool. Trace tool kind of is like, as time goes, it shows you on each line what is happening. And then the arc-list tool is also another Swiss Army knife where you can do things like plot a histogram of all the size, plot the distribution of the size of like kmalloc. That's called arc-dist for arguments. So here it will. So here this is a histogram showing that. Yeah, so those are the tools, and then I have some open discussion things we can talk about. But any questions so far or comments? Okay. So I have been interested in writing a tool to measure lock contention from the kernel, so a tool that could show you lock contention, and there is something already written that uses the Qtex call to identify that there is contention happening. The problem with that is Qtex cannot only be used for locking; it can be used for condition variables and all these other things. So the question is, how do you detect that the Qtex is a lock? Is there a way to do that? And one of the ideas floating around is we can unwind the stack and identify signatures that would show that it was a lock that acquired the Qtex. Only that is it's very user space specific, so it'll be like Android specific, where maybe we'll look at some of the art Android.
Yeah, so we were thinking of doing text lock and text unlock commands to mirror the lock PI and unlock PI commands, and make mutexes use those. Of course, then you'd have to fix your Bionic and all your other libraries, but that would instantly show you it would be a lock.
Yeah. It's not a uprob, so at that point, when the Qtex kprobe fires, you can look at the whole stack and unwind the user stack.
I mean, I understand that. I'm saying we're going to be unwinding kind of.
Yeah, I look for
Why
some.
not just put the uprobe on slow path?
Yeah, but then you have to know where to put the uprobe and.
You're going to have to figure that in anyway.
Why?
Having to right?
You put the uprobe on Qtex lock.
Okay. Yeah, but then there's people who use their own version of the lock, and they use Qtex to implement that. It's not just pthread actually. It turns out the Android runtime also has its own monitors which uses Qtex. So how do you detect those, right? So I was thinking like the stack stuff is a little fragile. Anyways, okay, can we do something else like maybe, is there anything else Qtex call can give us already that can tell us it's a lock?
Qtex is so.
Like timing or some parameters, can we like just do some history of how it's used?
You have to look at your C library and the Git to see if there's anything specific they do. Could be that the Qtex value could be hidden, but then again, it's just a hash weight queue.
Yeah, so you get,
they don't need to do anything specific.
yeah. So you might, the other ways don't care about the condition variable cases, and then you'll have those false positives. That will, then the other question is, can we provide more information about the user lock, or the lock that's in user space, just from the Qtex? But we only have the hash, right?
But also, if you look at the glibc mutex implementation, you'll find that it's actually a bunch of mutexes together. It's not just one mutex that does a mutex implementation.
Yeah, true that, yeah. We have to isolate those cases as well.
Yeah, so I haven't looked at Bionic in a while, but when I looked at it, it was all rather primitive and for the whole bit. And yeah, I have no idea what your JIT was. I know the some VM used to do some pretty complex. It's very hard to detect what it is.
Yeah. Are there other cases other than CVs and locks that Qtex is useful?
Well, the PI lock. PI lock is you can actually do this for PI locks because they have a proper lock PI and unlock PI, and the value is well specified as containing a TID, and it has 2 high flags.
That's the command Qtex commands you talked about?
Yeah.
Okay, so that's already done.
For PI, yes, but we were thinking about doing it for regular locks as well.
Okay, now I get it. Okay. Maybe we can just use the PI box Qtex then. If, will it do something different if you go?
It will do PI.
I mean, yeah, which is I understand that.
So, but if you use it on a regular skepfair task, it will not actually.
Yeah, so it's like the regular. Maybe I can then try to change it and see what happens. Use it and then. But there's always a possibility that some user application doesn't use libc and has their own locking stuff.
Yeah, luckily, you have control over most of that in Android.
Yeah, that's good. Yeah, the nice thing about being in the kernel and able to look at few texts is you'll look at everything, even if, so maybe you know that there's something bad happening, but yeah. But then you have the less information unless you use the lock unlock.
So what's the goal of the tool? Are you looking for something generic or
Like a performance issue related to lock and
the tool you're trying to do is, do you want it to be generic or Android specific?
generic. I mean, BCC tools are all generic for all Linux
Yeah.
systems, so we wouldn't want.
So then let's try to fix the one case first, right? GLC and
Yeah, good luck with fixing it.
Yeah, the thing is, we don't want a tool to depend on user space too much as well, because then what if there's somebody else runs the tool with a different user space?
then they get to fix
Like
it. They get to fix it.
Yeah.
Yeah, now few texts have very little use for.
Okay.
That's just how they
That's
are
just the
made.
design. So other than that, so we were thinking, coming out with different ideas for OSPM about what other tools we can write that might be useful. Like one of the things is maybe if we can combine the energy model with CPU frac and maybe have like a tool that shows you how much energy you consume between intervals. I think that would be useful.
No, this is as computed by the energy model, and then you can compare it to actual counter or something. I don't know.
Yeah. How does power talk work? Like, how does it know the power without an energy model?
It samples it from battery.
It what?
Deep precedence is
So
But then it does-
PowerTop looks at, as I will say, residency numbers. It looks at the RAPL counters and things like that. It looks at wake-up sources to figure out certain things.
Yeah, how does it know the watts and milliwatts?
RAPL.
Rebel, okay. Yeah, this will also make some automation easier, like if you have scheduler patch once the energy model is merged. And you break something, then you can easily run this without having this power hardware, right? That is harder to set up and automate. It doesn't have to be like very accurate, I guess, but more or less.
I guess we'll end up comparing like results of your model versus what I mean, what you want to do is to compare things made using the model against reality.
No, we're also having like a power top using the energy model without an external device to actually measure power might be nice because then I can use I don't know any device and
We have trace points. I mean, yeah, power trace. Take for example, because it contains some other, all the internal data used to this decision making, basically, and then you compare like that to where you can.
Right.
Like,
Yeah.
Okay.
get a trace and then so you could.
It doesn't need to use
Nice.
the energy model. I mean, it could just use
Yeah,
that.
other
Yeah.
Yeah.
But I guess the problem is that you must be careful because that changes that you get an energy model, that change on the ground that could cause energy differences, but you might also want to track the energy model. So you might want to be comparing for one kernel, one energy
Yeah.
model with another kernel and all that.
Yeah, you do. I mean, that's given like you assume that the energy model is correct and
Yet,
doesn't have a bug in it on its own.
well, I
Okay.
guess you can be like Kantan was saying, can be wanting to actually see how the energy model fits real power measures coming from outside. And then once you are confident that the thing matches, then you can use actually this thing to
So it'll probably be useful.
Yeah.
Okay. The other thing is, other than energy, like identifying other problems and like the scheduler itself, like goes on, like the issues that come up. Like it's load balancing, doing the right thing, or is EAS not hurting performance sensitive tasks by packing too much? Yeah. I'm just throwing ideas out, like like people can run these tools, and then at least you can. It's like a recipe, self-contained tool.
Like, one more thing is like, what is the scheduling overhead in schedule?
Yeah.
When the moment you wake up and like, this, how much time it to scheduler to enqueue the task and the
From wake up to enqueue.
Yeah.
Yeah, that there's like, if I understand, the sched waking and sched wake up.
So the difference between the
Yeah, that can be. So this is all completely open source. So feel free to send a tool like that does that. Then also, I think we had some talks on the deeper, getting into deeper idle and the wrong C state and stuff like that. So
Residency histograms. I mean, you got that residency. I would say, but that's
okay, you already have that.
we often like end up doing what information stuff. Histogram, not histogram, but like bar charts with residency.
Okay. Yeah, so one of the nice things about BCC is people use it a lot to like prototype a tool that is not, or like statistics not available in the kernel, and then if it's very useful in BCC, then they move that into the kernel. That's what I heard. So it's a good prototyping thing. I think.
In this case, they sort of are, not they don't include each other.
Sorry, I can't hear you, Charles.
In this case, because they're sort of there, but they're not. I think they don't include each other. So the frequency planning is just the last change rather than doing it.
Okay. Right. And then I tried this get time tool from Joseph, which he uses to do workload characterization, which I think Dhaval will talk some point, right? But basically, he looks at the wake ups and tries to generate an RTF JSON that works. So I tried that, and it didn't really work very well for me. So maybe it can be improved or something.
That was Joseph's thing, right?
It was yeah. Some of it works for him, but yeah.
All it does is takes how many wake ups and sleeps. That's done. So it's doesn't do the thread dependency.
It does. It generates mutex stuff in the RTF JSON, and it does that waker wakey chain stuff.
Does it capture the waker wakey?
Yeah. So the thing is, it's not 100% accurate. As in, like, it doesn't record exactly what scheduler events occurred. Like, tasks where woke up, ran, slept, woke up, ran, slept. It kind of like, until you hit a dependency, it just tracks the running time and the sleep time until you hit that dependency point. And so the RTF would be simple, like it shows run for this time, sleep for this time. So it's not accurate, but I think it helped him find some issues in Facebook. But if you want it to be accurate, then it's probably going to generate a very huge RTF JSON, right?
Yeah.
So
unless you're able to find some kind of periodicity in your systems, nevertheless, feeling each event.
yeah, ideally you want to record everything. Like I think perf does this sched record.
Yeah, Ingo wrote that a long time ago. It records a lot. I played was never really too hot, but yeah, it tried to do similar thing.
The replay works more or less.
Well, it does something. But like with a lot of things, if it just runs the tasks in busy loops, you lose a lot of what the actual workload does, memory access. I don't know. So he will play around with it for a while, but it was not really.
Yeah, true.
I don't know exactly what he's doing.
He's not doing that at all, yeah.
It's not only time, for example, time at this rate.
Yeah.
And also if it's interest a timer that will work it through or a straight timer.
So Chris had some patch for RTF that did the recording too, right? Is that are you aware of that?
What if it's passing an F trace or C trace?
Oh yeah, so he collects the traces and then post processes that to build the RTF.
I'm not sure if there is frequency.
Sorry.
I have an idea from Eduardo. So you could try to add prompts or similar to the magic node and look at the prediction, the predicted time duration, and then the actual speed time, and see, you know, if they are off or
Okay.
how much off they
So
are.
so we're talking about workload characterization problem, not that. But yeah, you're talking about the energy calculation.
To be able to estimate if it's a good, the prediction is correct or not.
Yeah.
Oh yeah, it's like a separate.
Yeah.
Yeah.
I mean, it can be, that kind of estimation is also used for workload tracking. Because you can tell if for particular workloads, how bad or how good your
Yes, if you have time, feel free to send a patch to write a tool to do that. So here's like all the details of all the links that I talked about, projects, the progress, and everything. Everything is public, and there's nothing internal or anything that all the work is public. The BCC guys are very nice, and then like they review stuff you send them, tools and all that, and they fix bugs and all. Um, and they're very active on that front. So it's pretty easy to develop BCC tools and discuss them and get reviews done and all that. Not that I'm saying it's the kernel doesn't have a good. What else? Thanks to all these people who helped me with everything. Brendan, Greg, Alexi, Strato, and Stash, I was seeing. Todd, thanks a lot for helping with the Android Dev tool. And then our kernel team is awesome. Thanks to them and the OSPM team. Thanks a lot. So yeah, if you have any questions, please ask.
Oh, yeah. Maybe one about the work browser overhead. What was the kind of tracing that you were doing?
So this is a ClearPro installed on finished tests, which it builds a histogram of all the slices, like how many times a certain slice duration occurred. So the histogram would have that. So the idea is that looking at that histogram, you can see it's like it got a very small time slice, and then it got very big time slices, and maybe there's some log contention. So it gives some idea about that. So every tool has a _ examples.txt where somebody actually shows a real problem that they were debugging with the output of the tool. So it tells you why the tool was written in the first place. So BCC makes that mandatory. So it's a very nice way of looking at how to use the tool.
So regarding all the ETL average, not average tracking, so usually what I'm doing, I'm adding my own trace points to make the track. Is there any way to do that with the eBPF? Can we output a large file with all this kind of trace?
Not at the moment, yeah. I guess no kernel modifications generally, and
No, the point is instead of adding this tracepoint, can't we use eBPF to track all the load average update?
yeah, you can use kprobes too.
Okay. And we can output that. Do we have any size limitation for the output?
No, you can specify the hash table size for the map, but no, I don't think
You can also have it stream into.
Okay.
yeah. All the Snoop tools actually use clock constant dividing.
It's kind of correlated. Can you run like multiple analyses at the same time? Like,
That is actually a good question. That's not possible right now, but Brendan and Alexi were working on fixing that.
not possible, meaning that you can load only one eBPF program.
time.
This program can collect different trace points.
Yes, no, it can't. Like that's one of the limitations of it. They're working on being able to load multiple programs, and maybe Peter knows more about the challenges with that. But if I remember, like you cannot use like per foot error route if you try to attach another BPF program.
Well, for the trace points, so I'll actually recently use raw trace points. I think that was managed by Steve or something like that. But, yeah, there was something. With the trace point. I have no idea what they do with multiple stuff. I don't really with that.
Yeah. And yeah, perf, like when I was debugging it, I saw perf was erroring out when you attach more than one program onto a trace point or kprobe or something like that. So you can,
I don't know.
there's some, yeah, so there's room for improvement definitely there. If there's use case, we can work on patch together for kernel and
Could you not just run that program twice? That's a dumb idea.
you could, but then you miss out on like, then you have to run the workload every time and then run the tool,
I
right?
mean, I know it's cumbersome, but
Yeah, if it works, then it's good. So,
Or only if you want.
yeah.
You want to have two programs, one to measure power and one to measure performance, and it's going to doesn't make decision. Then very can't really.
then you have to run them enough number of times, right? And
Then you get something which is average, doesn't tell you anything either.
yeah.
So it's useless if you can't measure multiple things at the same time. So is it that you can't load two programs at the same time, or is it you can't load two places?
I think it's both. This is like a little outdated, so maybe it was fixed recently. I haven't looked at the patches, but I think both have issues.
Serious limitation.
Yeah, we could fix it. I mean, it's not like there's no reason I can think of why you should not be able to do that.
But like what Peter was proposing, like having something at the queue time and the queue time, this kind of thing can also, like if you have different entry point in the scheduler and track something which is happening these
Yeah.
points with a
So
single.
yeah. So that's generally the idea. You have multiple kprobes being monitored simultaneously.
Okay, so possible to monitor different trace events.
Yeah, I have to put more thought into that and see how that works. You can try it and see if it works
Yeah,
on. And
absolutely.
yeah. Okay. Cool. Thank you, guys. Let me know offline if you have any questions or anything.
Thank you.